Pedro, you specialize in general relativity as a theoretical physicist and cosmologist. And your book on general relativity, you've used the title, The Perfect Theory. I wasn't sure whether that was direct or there was a touch of sarcasm.
No, I mean, I chose The Perfect Theory because I think it's almost a perfect representation of what general relativity is. Why do I call it The Perfect Theory? I mean, this is a theory that came out of this man, Einstein's head, almost fully formed at the end. I mean, it took him 7 years to figure it out, but it comes out. And
from when he had special relativity to general relativity.
From when he went from special, and he came out with this thing, and it's just this completely overturning the concepts that people were thinking about at the time. He brings in geometry in a way that they never did. It comes up with these equations which are incredibly compact. They're very simple. They're very clear interpretation of what they mean. They describe phenomena on all scales. Yet there's still so much to take out of them. You know, people are still trying to solve Einstein's theory of general relativity. They're just, only 10 years ago were people able to, for example, figure out what two black holes, which is a prediction from his theory, what they do when they collide and merge, and we've just seen them. And so stuff is constantly coming out of this theory. It's rich.
What are the different levels that we see general relativity working at, from our GPS to black hole? I mean, you're the expert. Tell me.
No, I can. So general relativity typically kicks in on large scales, right? We don't worry too much about it on the scale of this table, but it's a crucial part in our global positioning system. GPS. We need to have those corrections, otherwise our sat navs would get it even worse than they do. It has a small effect on the orbit of Mercury. The orbit of Mercury shifts by a minute amount every century, but that can only be explained in terms of the general.
And that was the first time that it was explained.
And that was the first time it was explained, was through Einstein's theory.
That was one of the first tests of it, in fact.
It was one of the first, exactly. It was one of the first tests. And as you start going to larger and larger scales, if you start looking at distant objects, the way that they collapse, the formation, the end point of collapse of stars, as you look at the expansion of the universe, all of these things can only really be explained in terms of general relativity.
But how can it be perfect without harmonization with quantum mechanics? Because that's the classic problem today.
So there is this issue, which is, general theory of relativity is very important on large scales. Quantum mechanics is what explains the microscopic. When you try and bring them together, there is a problem. Now, one has to be careful with that statement. We kind of understand the quantum mechanics of gravity pretty well. In other words, there is really no problem in harmonizing general relativity and quantum mechanics at some level. At the level in which we can measure things, it's absolutely fine. It's only when we start pushing at the extremes of general relativity that things become problematic. At regions of very high density, or near black holes. Not even near black holes, we're fine. We understand quantum mechanics. So it's only in extreme situations that we have this problem.
How about how each deals with the nature of time?
They're very different, right? So quantum mechanics is very much, 1 plus 3, you've got time and then you've got the other spatial dimensions. Again, we have to be careful there, because when the quantum mechanics that we use for particle accelerators is we don't use the normal quantum mechanics. We use this thing called relativistic quantum mechanics, quantum field theory. Okay, there you already have this kind of issue, that mixing of time and space in a way that you don't have in quantum mechanics. So you don't even need general relativity to start worrying about that.
Some of my friends would say that, would agree with everything you said, but at the end of the day, if we have to choose between general relativity, which you call the perfect theory, and quantum mechanics, if we have to choose of which is more fundamental, we will always choose quantum mechanics.
I think there are a lot of people who say that, and I think there are strong arguments to say that, especially because in the regime where we worry about the mismatch between quantum mechanics and gravity, we know very little about gravity. We know a lot about quantum mechanics. But there are people who would disagree. There are people who would say, no, actually, we need to rethink quantum mechanics. So I think there is. I think
would you be one of those?
I think we should believe a theory in the regime where we've tested it. We can extrapolate it, but we should be wary about extrapolating too far.